Hello everyone, this is Dr. Hopkins narrating the next in our series of videos for 472 this fall. And we're still working on first law. In this video we're going to kind of tie in some loose ends, add a couple new properties and so forth, so you'll see. Alright, so bulk property. So we're going to define these two new basically measurements, and they're measurements that you can make of any material. So we've been primarily focusing on gases. So we started with gases. We're going to use gases, partly because they give us a nice, easy equation of state. But these properties are properties of solids, alloys, so they're material properties. And oftentimes it's something you would use in engineering. So we're going to express them at partial derivatives. So we have the isobaric thermal, and sometimes this is isobaric thermal volumetric expansion coefficient, but I think it's just easiest to say this. It's alpha, okay, and it comes out to be this 1 over V, and it's the partial V with respect to T at constant pressure. So as we know with the partial derivative, what that means is we're making this measurement. To measure this quantity, we just would measure how the volume changes as we change the temperature under constant pressure, say atmospheric pressure. And then the second one we're going to introduce is the isothermal compressibility, kappa. Okay, so it's a minus compressibility as it gets smaller. So we're going to measure how the volume changes as we increase the pressure on it under constant temperature. And you can see that's represented in the partial derivative given. So these are mechanically measured and easy values to come up with. You just have to come out and do the experiments. And so what that means is there are tables of these for various materials. Okay, so let's use these and have a little fun with some partial derivatives. Okay, so part of the reason why we introduced these. So if we wanted to know, and we had our two quantities alpha and kappa, if we wanted to know how the pressure, we did not have one that had how the pressure and temperature relate to each other under constant volume. So we introduced that partial derivative. And then we can use the permuter relation of partial derivatives in the second part of this equation right here, where we relate these. We take this, it divides out into these two partial derivatives, and then we can invert this one, right? So we just use the inverter relation, and so we have, this remains the same, this is inverted. And well, you'll notice that if you substitute in our previous two quantities, the 1 over V's are going to cancel, the minus is going to cancel, and we're left with alpha over kappa. Okay, so here's a way that we can take something that's a measurement we might want. If we already have these known properties in a table, we could relate them back to that partial derivative. So this is another example in thermodynamics where we have this kind of mathematical construct which allows us to manipulate, from what we know to what we want to know. Okay, so we're going to do a little bit more fun. So that's the bulk property measurements. So let's remember when we did our heat capacity, we used the equipartition theorem to derive the fact that Cp is always greater than Cv, and we had a value Cp minus Cv is Nr, or Cpm minus Cvm was R. Now we can use, in this case we can't derive this, but we can use the second law, which we'll talk about later, to derive the following. So we have this quantity, which we had derived from the equipartition theorem. So now let's derive it from thermodynamic first and second law principles. And so it turns out that that is equal to T times these two partial derivatives. Now I'm using molar volume instead of just volume. And so then this property is alpha over kappa, like we did on the last page. And then this is alpha Vm, okay, because that comes from one of our previous bulk properties we defined. So this difference between these heat capacities is temperature times alpha squared Vm over kappa. All right, so here we have a direct link, an equation that links heat properties with bulk mechanical properties, alpha and kappa. So we can go both ways. We can figure out bulk mechanical properties from the heat properties, or we can figure out heat from the bulk properties. So this is a powerful tool we can use to go back and forth. Now we can also play around with this equation. We put our ideal gas equation in there and evaluate the partial derivative. So we put in 4p nRT over V, or nRT over, or excuse me, RT over VM, and for VM it's RT over P, and we evaluate these partial derivatives, and then you simplify it, and I'm going to let you do that math. I did not do the math on the page here. That simplifies to R, okay? If we do the same thing for a van der Waals gas, if we plugged in for P and for VM, although it's not so easy for VM, an expression for P for the van der Waals gas and evaluated those partial derivatives, you would get this value. I'm not going to show how you do that as well, but you would get this. So this is for a van der Waals. You can see how much simpler everything is when we use the ideal gas versus real gases. Okay, so we have a little bit more complicated expression. But if we take the limit as our molar volume, so if we let the molar volume expand to infinity or to larger molar volumes, what happens? It no longer acts like a van der Waals gas. And if we plug that in, do that limit that you learned in calculus for our VMs, you'll see that this will expand to basically R, okay, which is the ideal gas result. And the same thing if we went to really low pressures, if we plug them in, this limit goes to R as well. So you can see where the van der Waals gas and ideal gas kind of overlap in terms of these. So these are some partial derivatives, some bulk properties, heat properties. In the next video, we're going to talk about processes under different conditions and how to manipulate the equations to get information that you're after.